To approximate logs with a calculator, sometimes we can just plug them directly into a calculator. Most calculators have a log button, which will do base 10, and a natural log button, which will do base E. Some calculators have a log to a general base button, but some of them don't. And even if they have that, it can be a little bit confusing sometimes exactly what order you're supposed to write your arguments in. So it's good to have another way that we can evaluate any log using just one of these two buttons. So if we bring up our calculator and just look at these two simple examples, the log of 64, on this particular calculator I enter the 64 first and then hit log, and that gets me 1.806. And for the natural log of 3, I would enter the 3 first and then hit my natural log button to get 1.099 if I round that off. Some calculators might have you enter the log first and then the number, but we've already probably done a little bit of that at this stage. So just knowing how to take basic logs on your calculator is certainly necessary. For any other base, we use this formula that's called change of base. And it's actually a very simple formula. The way this works in general is that you're given something in base A and you choose base B. So you're changing the base from whatever showed up in your original expression to a chosen base, and most people will choose either base 10 or base E because those are the two bases that your calculator can handle. So if we take base 10, for example, that's the common log, so the 10 isn't written. The way the formula ends up looking is log to base A of x equals log x over log A. It's a lot simpler than it seems like it should be, right? The x, which starts out a little bit higher in log to base A of x, ends up in the numerator, and the base A, which starts out a little bit lower in our log expression, ends up in the denominator. We take log of A. These are both logs to base 10. So for example, log to base 2 of 12, I could rewrite as the log to base 10 of 12 over the log, again to base 10, of 2. And that will allow me to evaluate it with a calculator. So 12 log divided by 2 log is 3.585 if I round that off. Just to see that it doesn't matter what base you choose to change it to, I could have done ln of 12 over ln of 2. Even though the natural log of 12 is different from the common log of 12, and the natural log of 2 is different from the common log of 2, by the time I find this ratio, I will get the same thing. 12 natural log divided by 2 natural log gets me 3.585, right? So it really is your choice what base you change it to. If you prefer working with common log, go ahead and just change it to common log anytime you need a decimal approximation. If you prefer working with natural log, choose natural log. Or if you want to look at your expression and see if maybe it has some e's in it, then you'll choose natural log. Maybe it has some numbers that look like powers of 10, then you would tend to choose common log. So the log to base 20 of 2, I could rewrite as, go ahead and pause this and try it on your own and see if you get the same thing I get. All right, so I get 0.231. It's always a good idea to check and see if these seem reasonable, right? For example, if log to base 2 of 12 is about 3.585, that would mean that 2 to the power 3.585 is equal to 12, approximately, right? Since this was rounded off, it's not going to come out exactly right. Well, 2 cubed is 8, and 2 to the power 4 is 16, and this is somewhere between 8 and 16, so it seems reasonable, or we could try it out on a calculator. This one would be 20 to the power 0.231 is equal to 2. Remember, anything to the power 0 is 1, and 20 to the power 1 is 20, so that power should come out to be a fairly small fractional value between 0 and 1. That does seem to make sense. Applying this new method to longer expressions works in a pretty straightforward way. We just want to start with the log and rewrite it using the change of base within our expression. So log to base 7 of 10, I would rewrite, if I'm using base 10, I would rewrite this as log of 10 over log of 7. And the rest of the expression is still there. That's 2 times this, and then we have a minus 5 at the end. So I would bring in the calculator pretty much at this point, although I might also notice that the log of 10 is something that I can evaluate. So I don't have to make the calculator do this. That's simply equal to 1, the log to base 10 of 10. So bringing the calculator in, I can then just say 2 times 1 has no effect, divided by the log of 7, and then subtract off the 5 at the very end to get negative 2.633. I do encourage you to try to get the whole expression into your calculator rather than writing down decimal approximations along the way. As these expressions get a little bit longer, it is really the amount of rounding error that you're going to have in your final answer could end up being bigger than you intended. So even though I'm evaluating the log first, in a sense, I'm still going to get the calculator to store the result. So this here is the log of 14 divided by the log of 2. And I'm going to rewrite this whole expression with that now. 5 times the log of 14 over the log of 2 minus 10 all over 4. Even this one, I'm going to get the calculator to store everything as I go. If your calculator does a 2-line display, like a graphing calculator does, and like some much simpler calculators do as well, it does make it easier, but it is possible to do even if your calculator doesn't show you what you've entered so far. So for example, here if I start with 5 times, and I'll do the log of 14 divided by the log of 2, and then subtract off 10, that gets me the whole numerator, and now I can divide that whole numerator by 4 to get 2.259. Sometimes just getting to know your calculator is the best way you can spend time on a section like this one.